So is it working? Are you guys able to hear me? If you could just write something in the chat, I guess I could start. So is it working? Are you guys able to hear me? Yeah, so I guess we can start now. Just yeah. So I'll keep it pretty casual. I'm not going to include a lot of coding and all. It'll just be an overview of what you can expect from natural language processing if you're just getting into the field and want to do a couple of projects on it. And I'll just explain a few concepts and how you go about doing a natural language processing project if you really want to go into it, or even if you just want to have an idea of what to expect. So, first of all, what do we mean when we talk about NLP? So, as humans, we have been studying natural language processing for quite a period of time, or rather, we called it linguistics long ago when we were just talking about languages in general. But once we started using computers, right? Once we started using computers, things kind of changed, and we had a lot of tools that we could use in order to draw better inferences and make better use of these things. So then again, it raises the question as to how do engineers do NLP, right? So how we basically go about it is the very basic concepts of NLP are kind of like teaching a child what words are, or so when we want to teach language to a child, for example, we start teaching them words, then we move on to sentences, and so on and so forth. It's kind of like the similar for machines as well. So we teach them what words might mean, and then we go on to more complex things. We keep on adding more words, and then we get a sentence. We keep on adding sentences, then we get more and more complex structures. So, but that so. Uh, could anybody point out like where it stopped? I think it stopped here apparently. Uh, just drop it into the live chat. I'll just start once I get the confirmation so I can continue from where I left off. So I guess I was somewhere around here. So we can skip that, I guess. We've already lost a lot of time. This is just an overview of what kind of NLP tasks that we can do. So just moving on. So there's this problem unique to NLP. Unique to NLP, I mean that it does not exist in other machine learning problems, which is basically like, for example, if I want to train a model on how much is someone going to score in a test, then I'll probably get and give it a lot of features like solved for the preparation of test and the IQ of that person. And what you'll notice in this case is that all of these data are quantitative in nature. They are all numbers. Right. But in NLP, that's not the case. You have to somehow convert words into numbers before feeding it into a model so that the model can add it, subtract it, basically add, subtract words to each other and somehow they make sense. So this is something that is very hard to wrap your head around. Like, how can you add words and get something that makes sense? So that is something that I'm going to explain next up. So first of all, the main question is, how do we quantify words in the first place? So one of the most basic techniques and something that is used also to handle categorical data is one-hot encoding. So one-hot encoding is used when a data has values such as a color, right? For example, if you are classifying flowers and you want to figure out whether it's a female flower or a male flower or something like that, and you have a column which has values such as red, yellow, green, and you can't feed it directly into the machine learning model. So what you do is that you create three columns in this case because there are three values in that particular column, and you put one if that is true for that particular object, right? For if the flower is red, it's one in that particular row. If it's yellow, it's one in that particular row, and green if it's green in that particular row. So we actually do one hot encoding for the vocabulary basic NLP tasks, usually very useful, but in very small word sets, sometimes it's useful. But just imagine that for every single word that you have one column. It is very wasteful for the space, right? And just imagine that if you had want to add even one more column to it, you have to add like 10,000. If your vocabulary is of 10,000 words, you have to add another column, which makes the whole thing completely ridiculous. So it's very clear very soon that it's not tenable for more complex tasks. So for that, we have this thing called word to vec, and it's pretty self-explanatory. It basically converts words to vectors. So I'll talk about vectors, how word vectors are in general, what characteristics they have. But in this slide, I would kind of just explain how the machine figures out what word should have what kind of vector. So there are various and two main methods in which how we teach the machine what word will have what kind of vector. And the first one on the left, CBOW. So that one is basically like giving fill in the blanks to the to a machine learning model and telling it to figure out from the context what word will fill the blank, right? And the other one is the opposite to that, which is basically figuring out the context using a word. And the output we get from that machine learning model is basically a vector. I won't go into a lot of details. All you have to know is using these techniques, the model is able to come up with a vector which represents that particular word, right? So what does that vector look like? So these are two separate graphs which represent word vectors. The one on the left shows relationships between two words like man and woman, right? So you can see that on the x-axis there is barely any difference between man and woman because they talk about some people, right? It basically means people. But y-axis there are almost polar opposites, right? Especially if you look at brother and sisters, the value below zero is negative and the value above zero is positive. So you can see they are almost polar opposites in the y-axis. So you can see that y-axis talks about gender and x-axis kind of talks about what kind of person they are. So that's that. On the right side, you are matching companies with their CEOs. So how it works is kind of like Steve Jobs being synonymous with Apple, right? So in the y-axis, you can see there's not much variation. So in that sense, they are same, but in x-axis, they are very different. So that is basically how word vectors work. So earlier I was talking about subtracting and adding words, and it might have sounded kind of weird as to what it was. So like in this case, this is a coding example of how word vectors we can perform operation on word vectors. So if you look at the first coding snippet on line 6, we are adding the words woman and king and subtracting man to it. So if you think intuitively, if you subtract man from king from man, then you will get something like a ruler. And if you make it feminine, it is you would expect the answer to be something like a queen, right? So that's what we get. The bottom two snippets is something that I trained on a news data set. I was working on a task called fake news recognition. So it was a very small data set, and the answers are not very accurate and not very intuitive. But you can still kind of understand that we are able to get some semblance of semantics, some sense of meaning by adding some words together. By adding Clinton in office, I am getting things like presidential, nomination, candidate, which would be good description of a conjunction of the words Clinton and office. Again, adding the words with, Turkey and guns, which is basically like violence and Turkey. So it is telling us about the violent aspects of what we now in the topic of Turkey, right? So airstrike planes and all that. Basically, we are showing the top 10, top 5 matches for each. So that kind of gives us an idea of how we can actually put these vectors and perform machine learning tasks on them. So now we know how we can turn words into vectors. So I guess the next natural question is, what kind of models do we use these word vectors with? So one of the most basic and very typical example of NLP models is Bayes theorem, which basically naive Bayes is the algorithm, and Bayes theorem is used for that algorithm. Bayes theorem basically talks about probabilities, but not in the common sense. In the common about probability, like given a fair die, fair meaning that any number it has an equal chance of occurring, the probability of fair die getting a particular result and so and so. But in Bayes theorem, we turn things around a little bit. What we do in Bayes theorem is that we take a particular event, like we say that this has already occurred, and what are the chances that if this has occurred, the particular situation is this. So I guess it's kind of hard to understand that way. So just take an example. We have all heard about MS-370, right? What we do not remember is that around 2009, there was another flight called Air France 447, and it had crashed in June 2009. However, it was found a few years later using the help of Bayes' theorem. So what the people who used the theorem did was they used all the data that they already had about the plane and use that probabilities of what is the probability that if this happened, plane would crash there, and using those probabilities they kind of made a map of where the plane could possibly be. And once they started using that map and resumed the search, within 1 week they were able to find the wreckage of the plane in 2011, which was basically 2 years after the plane had crashed. So basically the algorithm was so effective in figuring out the location of the plane that it accomplished something in a week, something that was accomplished in 2 years. So that's how Bayes theorem is, even though it's so basic. We studied it in class 12, but it's still so useful. To give a better example on how it works and how it's different from typical probability is, for example, if I go and get tested for cancer, right? So normal probability will just give me the chances that in given a population, what is the chance that I have cancer, which is probably like 0.1%, for example. But Bayes theorem will more likely tell us that if I test positive, what is the chance that I may not have cancer, for example. So in this case, there is something given, and given that particular situation, what is the likelihood of something happening? So that's what Bayes theorem is actually about. So how do we use Bayes theorem in NLP? Right. So here you can see these sentences, and there is this label called spam and ham at the end of it, which basically spam means that it is a spam and ham means it's not a spam. So that's what they call spam classification in NLP. So at the bottom, we can see that each word has associated probability of occurring in a spam email or a non-spam email. So using these particular informations that we have, that how often that a word occurs in a spam, and how whether that word is occurring in our email and how often it is occurring, all these things combined will give us a likelihood that whether or not that email is a spam. Right. So till now, we are able to make some analysis based on a particular word. But we know that in NLP, we do much more complex things than that. Like we use machine translation or chatbots, and of course, they don't focus on singular words. If they focus on singular words, they won't be able to make sense of sentences, right? So how do we take the next step and basically make sense of phrases in the first place and then go on to sentences? So to make sense of small phrases, right, we can use recurrent neural networks. And an example would be like 2020 would be my year, or so I thought. If we wanted to analyze it word by word, we would not be able to realize that the second part of the sentence is connected to the first. And any analysis based on that would be faulty, right? These two parts are connected, and without the first part, the second part will not actually be able to stand on its own. So in this case, we use recurrent neural networks. So recurrent neural networks is can be represented by this, and I know it's kind of complex, but I'll try to make it really simple. I won't go into any of the details what this notation is talking about. I want you to focus on the words that are in there in the bottom, right? And each word is acting as an input to, for example, first word is input to A1. But when we enter the second word in A2, we can do A2 as well. We see that A1 is input to A2 as well. So we see that previous word is also being we are taking input the second word. So now we have two words as input. So we can take these two words in conjunction and we can know that before lacking we had this word completely. So now we can make sense of both. Now the third word has the previous two words as its components, so we can the model is able to look at all three words together. So as we go on, you can see how it can take into consideration words that had occurred previously when it is taking into consideration the current word as well. But the problem with RNNs is that it cannot go on forever. Like it can take into account 5 words, 6 words, even up to 10 words, like in this example. But after a point of time, it starts losing its memory. So it basically, even its short-term memory isn't really good. So for that, we have what is called LSTMs, which has a very self-explanatory name, if you ask me, which is like long short-term memory, right? So it has short-term memory, but it is quite useful for cases in which you do need short-term memory. So this picture I took it down from a YouTube video. If you want to know which video it is from, I can give you the link because this video was really helpful in getting me to understand how LSTMs work. So what LSTM does is that not only does it recall from a previous word, it also decides what words are really significant. For example, let's take the sentence uh, Harry and Hermione went for a walk and they talked about various things, right? So, if you notice, when performing machine learning tasks, the second sentence has the word they. So, it might want to know what they is talking about, it does not really care for the part where it has or in. These kind of words do not really have much relevance, so there's no point in carrying it down the line. So talking about the structure of um, uh, the LSTM. So you see that there's this weird thing and there's this weird thing. So these are neural networks, and I'll explain to you what their purpose is in just a bit. And this is a gate. Gate is basically something that allows or stops things from going through, and this is basically a join which joins memory and prediction together. And I'll explain what all these terms mean in just a bit. So first of all, from the left, new information comes in, right? Like a new word, and it goes two places: the top neural network and the bottom neural network. The bottom neural network is tasked with making predictions with the new word, and forwarding that prediction ahead. The top neural network is tasked with figuring out whether this word is relevant and whether it should be remembered. Once it has figured this out, the memory gate decides whether it should go ahead or not. If it decides that it should go ahead, it joins with the prediction and it goes ahead to the next input, and also it is taken into consideration once again. So basically, that's how LSTMs work, and we are able to do the things such as machine translation and things that involve more complex